Hi guys, next we are going to start with the analysis of our trusses. See, generally here in the analysis of trusses, our aim here is to find out the nodal displacement, then stresses, and then reactions at the support. So that is our intention. Now you can look at the image where you have a truss element shown here, which is subjected to load 20 kilonewton and 15 kilonewton. If you look at the specification properly, this 15 kilonewton is moving along the x direction and this 20 kilonewton is acting along the y direction. So generally you give the node numbering in the counterclockwise direction, means okay, and always take a reference system. In general there will be no reference system will be given. So how you are going to take a reference system means ensure that your left bottom is as a reference or as a origin so that all the coordinates will be in positive. Now if you start your node numbering in the counterclockwise direction, so this is how the node numbering will be: node number 1, node number 2, node number 3. So this is node number 1 will be your reference, or this is your origin. Okay, now the coordinates of node number 1 will be generally 0, 0, because it is a origin, it's at the origin. Now in order to reach node number 2, okay, you are going to travel only in x direction, so that is why the coordinate values of node number 2 will be 4000, 0. From 1, in order to reach node number 3, you are going to travel in your x direction by 4000 and in y direction by 3000. So the coordinate values or the coordinates for your node number 3 will be x is 4000, y is 3000. So this is how you are going to have a coordinate system. And okay, we are going to start with the problem. And before going to this, you need to understand one more thing. This analysis of truss is similar to our bar elements. Okay, if you have a look at this, before going to this trusses, you need to understand one more thing, that is a different types of coordinate system, generally what we use in FEM. If you have a look at it, you have a coordinate system over here. This is a x direction, this is a y direction, and this is a z direction. We generally call it as global coordinate system. Okay, this is a standard reference system what we are going to use. And here you can see coordinates xm, ym and zm which is generally called as local coordinate system. In these two images you can see local coordinate system is a coordinate system which is taken according to a person or according to a image inclination. See here, along the longitudinal axis of a pin, he has taken the coordinate as xm. With reference to xm, he has taken ym and zm. Okay, so you can see here, this is not a standard reference system. xm, ym and zm, this is not a standard coordinate system. This is generally called as local coordinate system, which is going to vary from one problem to other problem. See here, the local coordinate system in this problem is having a different inclination, and here it is having a different inclination and directions. Okay, so based on this concept only, we are going to do the analysis. What is that concept means? The truss element is similar to your bar element in local coordinate system. Okay, so we are going to use the same element type for solving this truss problem. Okay, so we are going to go with this preferences, structural, H method, okay, preprocessor, element type, add, edit, delete, add, see link element 2d power 1, okay, close this one, then go to real constants, add or edit or delete. Before going to this, let me check what is area. See, he has given area for all the three elements as 2000 mm square, and also the node numbering has been done in counterclockwise direction. Ensure that you are going to do your element numbering also in a counterclockwise. So this is your first element, this is your second element, and this is your third element. Okay, all the three elements will be having the same area of 2000 mm square. Okay, is it necessary for me to enter area thrice? No, it's not necessary. One area will be, if you enter the area once, it's NF. Okay, so the area is 2000 mm square. Okay, close this one. Material properties, material models, structural, linear, elastic, isotropic. Young's modulus is 2E5 and Poisson's ratio is 0.3. Okay, material, exit. Generally the Young's modulus will be given, the Poisson's ratio you have to take it on your own. Okay, go with modeling, create, nodes, inactive coordinate system. Before going to this, see, that's what I was talking about, the nodal coordinates. In this image, if you have a look at it, this is the origin. So origin means the x and y value will be 0, 0. Now if you have a look at it, see, node number 1, I'm going to enter 0 and 0. By default, if you're not going to enter any value also, it will be considered as 0 itself. And node number 2. So node number 2 is at a distance of 4000 mm along x direction, and y value it is 0. So apply. You can see that node has been created on the screen, and click on node number 3. X is 4000, y is 3000. Just give OK. When you are entering the last node, ensure you are giving OK. Then create the elements auto numbered 2 nodes. Since all the 3 elements, look at this image, since all the 3 elements is made up of same material and having a same area, so no need of going for element attributes. Okay, this is one. Whenever you have different areas and different material properties, you need to go for the element attributes. Since all the 3 elements is made up of same material, so and having the same area, it's not necessary. Okay, click on through nodes. Okay, select 1 and 2, apply. Select 2 and 3, apply. Select 3 and 1. Okay, when you are joining the last element, okay, you are going to give OK. So I think I've done with my modeling part. Next, so what I need to do is I need to fix this. Look at the diagram carefully. Okay, see, this is completely fixed. Node number 1 is completely fixed along all degrees of freedom, whereas at node number 2 you have a roller support, means you can pull this. When you pull this along the x direction, it is free to move along x direction. The support has been given only along the y direction. Okay, so this you are going to do it in this loads, define loads. Click on define loads, apply, structural, displacement, on nodes, select node number 1, give OK. You can choose all degrees of freedom. Okay, now again click on the same command, on nodes, select this one. Okay, see, roller support, how you are going to give here is, okay, you support it only along y direction, means you are fixing it along only y direction and it is free to move along x direction. So this is how the fixing will be done, and this is how you need to ensure that this has been fixed along only y direction. After this, you can see this, you can see the point loads. Okay, force or moment, on nodes, select node number 3, because at this node only you are going to come across the force. You have 2 forces. One is one force is 20 kilonewton, which is moving along the y direction, that to negative y direction, and this is moving along the x direction, that to positive y direction. So what you are going to do here is you click on fx and enter 15,000 or 15E3, both are fine. Okay, give OK. So this is how the load is going to happen. Load is going to be applied. So in the same node number 3, give OK. You choose your Fy value. Now ensure that you are going to give 20,000 minus, because it is moving towards negative y direction. See, this is a load which is moving towards a negative y direction. Okay, so this is positive x, this is positive y, and this is positive z, perpendicular to my screen. Okay, so this is how your load is going to act. Close all the commands. So this is a pre-processing stage, means all the inputs has been given. Now click on solution, solve, current ls, give OK. In case you do any mistake, it will be highlighted here itself. No, solution is done. Now go to the general post procedure. Directly always go to the element table, define table, add by sequence number ls, 1. Okay, ls, 1. Close this one. Once you are done with this, as usual, you go to the list results. First, go to the nodal solution. Yeah, here you need to take displacement vector sum, because it is click on DOF solution and you choose displacement vector sum, because this is a plane element, so the displacement will be happening along both x and y direction. So you should not choose either x or y, you need to choose displacement vector sum, which is going to cover all. Okay, you can see you are going to get the displacement along x direction, you are going to get displacement along y direction, you are going to get displacement along z direction. Okay, so that is since that direction is not been loaded, so 0. So this is how you are going to get your displacement table. You are going to copy down this table. Okay. After this, you are going to go for element table data. If you click on this ls comma 1, okay, you are going to get the stress table. Okay. See, in the element 1 there is no load, and if you just have a look at it, look at the diagram. See, interpreting the results is a major thing, which is we can go to get the results. That's not a big deal. Okay, if you have a look at this, see, element 1, because there is no load which is acting on it straight away, so the stresses on that one is 0. But whereas element 2, it is completely subjected to compressive loads, so that is why minus 15. And whereas element 3 is subjected to a tensile load, that magnitude is 9.3750. Copy down this table. Okay, particularly this, which has been highlighted. We're going to copy down this table as well. Once you are done with this, next one is the reaction solution. We are going to choose all items as usual. Okay, so see, wherever the nodes are fixed, at that point only you are going to get the reactions. So this is at node number 1, you are going to get reaction along both x and y directions. Since your node number 2 is fixed only along y direction, you are going to get displaced, you are going to get reaction only along y direction. So that is why this fx has been left blank. That doesn't mean 0. It is 0. Yeah. So this, the advantage of FEM is that you can visualize the results, contour plot, nodal solution, displacement vector sum. Okay, you can see the deform shape, how exactly the deformation is going to happen. See here, blue color indicating there are no displacement of element 1. So that is why whenever there is no displacement, obviously there will be no stresses. Okay. If you want to see the stresses, click on the line element results. Okay, see, this is how the stresses is going to be occurring. Okay, here blue color is indicating the compressive stress, and red color is indicating the tensile stress. Okay, if you want to see this in 3 dimensions also, you can see this one, size and shape, on plot, click on elements. Okay, this is how it's going to be. Yeah. And the moreover, why exactly I am going to take ls1 all the times means here you have a command in 6 tutorials. See, in the element reference you can see different types of elements. Okay, see, this is the element we are choosing. This is how it is going to look like. This is how in local coordinate system. See, this is global coordinate system, x and y. This is a local coordinate system. Okay, why exactly we are going to give ls comma 1 all the time? So here is a library, here is a list of commands what we are going to use. See, here you can see I have given ls comma 1. See, what do you mean by this ls? The description has been given by the developers, software developers. ls comma 1 means you are going to find out the stresses along axial direction. Okay, see, generally whenever you click on solve solution current ls, see, there are n number of iterations will be happening, and you are going to get these many results. Okay, see, these many results you are going to get, which is not necessary for us. So the necessary result will be taken by giving a codes like this, ls comma 1. Okay, so that is a purpose why exactly we are giving ls comma